Hello. Now today we're going to look at section 6.3, which is projection at any angle. So in the last video we looked at how to deal with horizontal and vertical components of a projection, and we looked at the concept of ux and uy for the horizontal and vertical components of the initial velocity. So we're going to take that a bit further now and apply it to solving more complicated questions and looking at analysing any kind of projectile really. So the few things you need to bear in mind. Generally, your kind of simplest example of projectiles is something going from a horizontal plane, projected up, and then lands back on the horizontal plane, and that's how we would represent it like this. So this part here is the horizontal plane, and the parabolic line, the parabola here, is the line showing the flight of the projectile. So now I'm going to mark on my velocity, my initial velocity, u, and remember, like we talked about in the last video, that velocity u can be split up using its angle of elevation alpha into u cos alpha going horizontally and u sine alpha going vertically. So we have u and alpha like that. Now, one thing I wanted to point out here is that at any point along this flight, we could work out the velocity that we were travelling at that moment. If you think about this intuitively for a second, if you throw a ball up in the air, initially you throw it at a certain speed or velocity, and as it goes up, it will get slower and slower and slower and slower until it reaches its greatest height. And then it will get faster and faster and faster, and it'll come back down to Earth. But at any point along that flight, if we were to say take this point here, if I draw a tangent to the curve at that point, then that tangent represents the velocity at that point. So let's call this v1 for this point here. Now let's come to this point over here. This time it's pointing down, and that represents the velocity at that point, so I'll call it on v2. When it hits the ground, if I draw the tangent, you can see the line's much steeper, so we know we're going faster at that point. So this one would be, say, let's say v3. I'm particularly interested in this point, the greatest height that we reach. If I draw the tangent there, you'll notice that it's horizontal. Well, what does that tell us? That tells us that at this greatest height point, let's call it v at greatest height, so I'll do a little subscript GH there, we are travelling horizontally, but we are not travelling vertically. There's no vertical component there. So that gives us a really important principle, and that is that at the greatest height, our vertical component of velocity, Vy, is 0. So we're only travelling horizontally, we're not travelling vertically at all. So that's one important point. So there's a few other bits of vocabulary that you need to know. So from when you start to when you finish, the total horizontal distance travelled is called the range, and the time it takes to get from there to there is called the time of flight. Now, the only other thing I wanted to point out at this stage is sometimes you might want to model an example where instead of throwing a ball from the horizontal ground, you instead project it from up high. So this example might be something like throwing a ball off a cliff, for instance, or throwing a rock off a cliff into the sea, something like that. Now, you still have the same idea. So you still have your initial velocity u, and it's still split into its horizontal and vertical components using alpha, just like we did over here, u cos alpha horizontally, u sine alpha vertically. We still can work out our point where we reach our greatest height, because at that point we are travelling horizontally, but we are not travelling vertically. So our x component of velocity exists, but the y one is 0. But it's worth pointing out here that we still fit this parabola shape, because every projectile flight fits a parabola shape. It's just that if I kind of continue down there like that, our story of this journey, if you like, starts higher up along the parabola, but then the parabola continues on down below there. We still have the concept of the range, which would be this horizontal distance here. The range is always strictly horizontal. So it's not, although we started at this point, that line there, that diagonal one, that's not the range of flight. The range of the flight is horizontal. So bearing all that in mind, let's have a look at the first example. This is example 6. And we're told that we have a particle P, which is projected from a point O on a horizontal plane at 28 metres per second and an angle of elevation of 30 degrees. And we know that this particle strikes the plane at another point called A. So first of all, we draw a sketch. Nobody attempts these questions without a sketch, not even your teachers. So don't you try, because if you do, you'll get yourself in a mess. So here we go. We're on the horizontal plane, we go up and it comes back down again. This is point O, this is point A. Obviously this should be a perfect parabola, but it's only a sketch, so you can let me off that one. Now let's mark on initial velocity of 28 metres per second and angle of elevation is 30 degrees. So we've got that bit there. Let's put U equals just to make that really clear. And that's all we know at the moment. So bearing all that in mind, we can go ahead and answer these parts of the question. So the first one is asking us to find the greatest height reached above the plane. So it's asking us to find this height here. I'm going to call it Y. For that point here at greatest height, compared to O, we have a horizontal distance we'll call X and the vertical distance we'll call Y. Now, for every single one of these questions, we start by writing out our SUVAT, but using the horizontal and the vertical components of everything where that's relevant. So S is X, Y, horizontal, vertical. U is the horizontal component of this, so that's 28 cos 30. And then the vertical component, so that's 28 sine 30. V, we don't know the horizontal speed, but we do know that the vertical speed is 0 because we're dealing with this point here. Let's mark it on, shall we? There we go. V0. I could write Vx here if I like, but it doesn't really matter too much as long as I put a letter for it or a symbol for it. Now, A, in every single one of these questions, our acceleration is always acceleration due to gravity. And remember, we've talked about this before, anything going upwards is positive, anything coming downwards is negative. And acceleration due to gravity is 9.8 metres per second vertically down towards the Earth. So this always has a horizontal component of 0 and a vertical component of minus g, where g is 9.8. And then finally, the time of flight, we don't know that, so we'll just put t. So we've got to think about our equations of motion we've got to use S because we need to find this value Y here, that's the greatest height. So we're looking for this. We've got to use U because we know it. V, we know bits of that. A, we know. We don't know T. So we want to use an equation that doesn't involve T. So my equation is V squared equals, V squared, that's better, equals U squared plus 2AS. Now before I plug anything into this, just looking up here, I want to tidy this up a bit first. Cos 30 is root 3 over 2. So let me show you on the calculator. 28 times root 3 over 2, that's 28 times by cos 30, that's 14 root 3. And do the same thing with this, sine 30 is a half, so we've got 28 times a half, so that's just 14 there. So I'm going to tidy that up before I plug it in. Now let's plug what we can into this calculation. So we've got Vx squared and 0 squared equal to 14 root 3 squared and 14 squared, that's my u squared there, plus 2 times A times S. Now, remember from previous examples, we have two rows of equations here. This row, that's our horizontal motion. This row is our vertical motion. Now, because I want to find out y, I'm going to take the second row. So we've got 0 equals 14 squared minus 2gy. So that gives us 2gy is 14 squared, which is 196. So now let's take our 196 and divide it by 2g. So that's 2 times 9.8. I can type it in the calculator in line like this, or I can use the fraction button, because I'm doing it, ultimately I'm doing this, aren't I? Y equals 196 over 2g. So let's do it like that. 196 over 2 times 9.8 is 10 metres. Now I need to point something out here. You know, we use g as 9.8. G is actually more accurate than 9.8. Some in physics, for instance, I think people who do physics A level use 9.81. It can be measured more accurately than that, but in maths A level we use 9.8. Now notice therefore that we are only using G correct to two significant figures, 9 and the 8. That means that the minute we put G into any of our calculations, they are never more accurate than two significant figures. So although this 10 is coming out like that, it's not actually exactly 10, but we have to write it to two significant figures. Now, in your exams, they will accept 3 significant figures, but if you put any more accuracy than that, it's wrong, because that's actually incorrect. It's not accurate. So you have to give everything to 2 or 3 significant figures. I mean, we generally say across all of A level, give it to 3 SF, and then you'll be fine, and you know you won't make you'll get the answer correct unless you're told otherwise. So 10 is fine there. Now, for the time of flight then, this time I need to do my suvat again, because this set of suvat was done for this point here, from O to that point there. For the time of flight, I'm interested in the journey from O to A. And because I have it's a different journey, it's not just O to the top here, it's O to A, I'm going to do suvat again. Some of the things will remain the same, so this won't change. This changes because we're not interested in the greatest height now. I don't know that one actually, so I don't know anything about it. What I do know is as I come into this point here, I've definitely got a horizontal and vertical component, haven't I? Because this is going at an angle. So I don't know anything about it at the moment. I could just write Vx and Vy if I wanted to. A is still going to be 0 minus g, because that always is the case. And t is actually what I'm interested in finding this time. Now, let's come back up to S. This is the one I'm particularly interested in now. From O to A, let's think about the displacement. We travel a certain amount horizontally, so let's call that x. But from this point to this point, what's the change vertically? They're on the same level, aren't they? So the vertical change is actually 0. Because from here to here, there is no vertical change in displacement. So now we need an equation that uses S, U, A and T. I want to avoid V this time because I know nothing about it. So S, U, A and T is this equation. S equals ut plus half at squared. Let's plug in our vectors. Now we've got 2 rows of equations again, the horizontal row and the vertical row. Now let's have a look at which one of these is going to be most useful for us. If I use the top row, I would have x equals 14 root 3t plus 0. So I'd have one equation with x and t, 2 unknowns. It's no good for me. What I want is the bottom row, because on the bottom row I have 0 equals 14t minus half gt squared. And the only unknown in that equation is t, because remember g is 9.8, we know that. So let's put in 9.8, shall we, just to make this a little bit easier to work with for now. Half of 9.8 is 4.9. And we have a quadratic equation. To solve this, we're going to factorise it by taking out t. So it gives us 2 solutions. Either t is 0 or t is 14 over 4.9. That gives us 20 over 7. Now remember, although it looks like we have an exact value, it's not exact. because we've used g in this calculation, so we have to give it to 2 or 3 significant figures. So I'm going to give all my answers to 3SF. So that gives me t is 2.86 seconds. Now, why have we got 2 answers? Well, if you think about what we were working out when the vertical displacement is 0. That's at the start, so that's t is 0, or at the end, and that's when t is 2.86 seconds. So our time of flight, which the question asks for, is 2.86. Now finally, we're asked to find the distance from O to A. We've actually done all the hard work for this already, because we already wrote out SUVAT for O to A, and we identified this equation. And the thing we're trying to find currently is x, what we call the horizontal distance. And if we take that top equation, so this one, we have x equals 14 root 3t plus half times 0 times t squared. I'm going to write it out just so you can see. But of course, all of that will be 0. So we just have x equals, I missed off the t, that was better, 14 root 3t there. We've already worked out t in the previous example. I've still got it on my calculator. So I'm going to take that answer and I'm going to multiply it by 14 root 3 to give me 69.3 metres to 3 significant figures. The book tells you it's 69 metres because the book gives it to 2 significant figures, but like I said to you, 2 or 3, 3 is acceptable, 2 is probably a little better, but 3 is absolutely acceptable. The reason I'm saying 3 is if you just do 3 across the board for stats and applied and everything, you'll always be okay. Now, we talked in quite a lot of detail about what came up in that one, so let's have a look at the next example. And hopefully now I've illustrated the points, we'll be able to go a little bit quicker through it. So we have a particle being projected from O, and it tells us in the question that O is 42.5 metres above the horizontal plane. So this is an example of, say, throwing a rock off a cliff into the sea, and we're above the horizontal here. So let's do ourselves a sketch. Here we go. We know that. I'm going to mark on the distances. What we're told, that's 42.5 metres, so that's that bit. Let's draw my projectile. Something like that. Now, let's use this bit a second. It's projected at v metres per second. They like to confuse their v's and their u's. So v metres per second at an angle alpha. So if we mark that in, that angle there, not alpha, theta even, get your letters right. So angle is theta, and we are told what theta is, but we're told it kind of a roundabout way. We're told that tan theta is 4/3. We're also told that the particle P strikes the plane at the point A here after 5 seconds. And so the time of flight there is 5 seconds. Let's make a note of that. So first of all, we've got to show that this initial velocity v is 20. So from O to A, let's write out SUVAT. So you've got to be really careful here. From the start here, remember anything going upwards is positive, anything going downwards is negative. So from here to here, we've travelled a horizontal distance, unknown, but a vertical distance from here down to here of minus 42.5. And we have to have the minus to show that we end up below where we started. So our initial velocity, we still have our horizontal and vertical components here. So we've got v cos theta and v sine theta, using v because that's what we were told the initial velocity was. When we hit the ground at A, it looks like this coming in. don't know anything about it, so I'll just call it, do you know, I don't like the fact we've got a capital V here. If I write a little v there, it's going to get confusing. So I'm just going to leave that for now because I don't need it. The question's not asking about it, so I'm just going to leave it blank. My acceleration due to gravity is 0 minus g, and the time of flight was 5 seconds. So we've got S, U, A and T. So just like example 6 in the last two parts, we're using S equals UT plus half AT squared. Let's plug in what we know. Missed the T off there. T is 5, so for now I'm going to put 5 there and then 5 squared there, and we'll deal with the multiplications and things like that in a moment. Now, cos theta and sine theta, I don't like the fact we've got them as unknowns, so I'm actually going to work out what they are. Let's do this up here out the way for a second. If this angle theta is something like that, let's have a right angle there. Tan theta is opposite over adjacent. So we know that the opposite is 4 and the adjacent is 3 in this triangle. Using Pythagoras, 3 squared and 4 squared, this gives us 5 here. So from this I can write down what cos theta is, because cos theta is adjacent over hypotenuse, so that's 3/5. And sine theta is opposite over hypotenuse, so that's 4/5. So that means down here I can plug in the actual values of 3/5 and 4/5 for those. So let's write out both equations this time. Horizontally, we've got x equals cos theta is 3/5, so that's 3/5 v plus half times 0 times 5 squared, so that's just 0. And vertically, we've got minus 42.5 equals, actually no, I've done it again. I missed out the 5. V times 3/5 is the 3/5 v times 5. So that's just going to be 3v, because of divide by 5 and the times 5 cancel each other out. So coming to the second row, minus 42.5 equals sine theta is 4/5. So we've got 4/5 v times 5. Don't miss it out. And then minus half times g times 5 squared. Let's tidy this one up a bit, shall we? Minus 42.5. The 4/5, the 5 and the 5 there cancel each other out, so we've got 4v. And then let's work out this one. Minus half times by 9.8 times by 5 squared gives us minus 122.5. So let's take that to the other side. So that gives me 80 equals 4v, and that therefore tells me that v is 80 over 4, which is 20 metres per second. And that was what I had to show. So I've done that. Now, the reason I wanted to write out both equations here is because I knew I was going to need this top one for part B. So in part B, it asks me to find the distance from O to A. That's asking me for this diagonal distance here. Now, you'll notice that I've got a right-angled triangle there. Whenever I have a right-angled triangle, I can use Pythagoras. So I know the 42.5, I just need to know this horizontal component here, this x, but I've got an equation for that right here. X is 3v. So let's carry that across. We know that v is 20 from working out that one. So x is 60 metres. Let's fill that in, shall we? Overwrite my x there. So now we can use Pythagoras to find the distance OA, because OA is going to be the square root of 60 squared plus 42.5 squared. Don't need to worry about the negative here, do I? Because I'm squaring it. And then 60 squared plus 42.5 squared is equal to 73 point, and the square root thereof, of course, is equal to 73.5 metres to 3 significant figures. So that's example 7 done. Example 8, we have now got a little bit more to think about on this one. We've got a particle P projected from a point O at 35 metres per second, an angle of elevation of 30. How long is it 15 metres or more above O? Let's think about what this is asking us. As always, we start with a diagram. Do not do any of these questions without a diagram. So here's our point O. Initial velocity there. Oh, that was a rubbish tangent. Imagine that's tangent. Is U is 35 metres per second, and the angle there is 30 degrees. So what I'm particularly interested in here now is this bit. How long is it 15 metres or more above O? So let's draw ourselves a line like that and say that this height here is 15 metres. So that point there, 15 metres. All the way along, we are 15 metres above O. And the question is asking us, for how long do we stay 15 metres or more above O? So from here to here, what's that time for that section of the journey? So let's have a think about this. As always, we're going to set up our component parts for each of the parts in the equation. And what I'm interested in is from this point to this point. So I'm going to call this point P and this point Q. So I'm setting this up. Actually, do you know? No. What I'm going to do is I'm setting this up from O to Q from the start, mainly because it's the start where I know this bit of information here. So for S, we have no information horizontally except vertically. We know we're dealing with a height of 15 metres above the ground, or above our initial point of projection. For U, we have 35 cos 30 horizontally, 35 sine 30 vertically. Then for V, I don't know what speed I'm going at here or here, no idea. I'll put a question mark there. For A, it's always 0 minus g, and the time I'm actually interested in. Now, so I'll put a t there. It's worth pointing out that what I'm doing here is I'm working out the points where S is 15. So S vertically is 15. So 15 metres above O. So this is O to Q, but this also fits O to P as well, because both of those points have this one thing in common. They are where we're 15 metres above O. So S, U, A and T. That's this equation again. S equals UT plus half AT squared. Let's fill it in with the vectors. So we have got 35 cos 30. That's 5.39. You know, I'm going to keep this for now as, no it's not. Oh, my calculator's not in degrees. Let's go to degrees. There we go, that's better. So 35 cos 30, I want it in third form, so we'll just write it as 35 root 3 over 2. And then 35 sine 30. Sine 30 is a half, so that's just going to be 35 over 2 there. T, and then plus half times 0 minus g t squared. Let's do our horizontal component, our horizontal equation. X equals 35 root 3 over 2t, and then plus half times 0 times t squared, so that's just 0. Let's do our vertical equation. 15 equals 35 over 2t minus a half gt squared. I've got a quadratic equation again with only one unknown, t, because g is not an unknown. Let's put half g in. Half times 9.8 is 4.9. So 15 equals, I'm going to write this one now as a decimal, so 17.5 t minus 4.9 t squared. Now I'm going to solve this quadratic equation by bringing everything to the left and making it equal to 0. So that gives us this. And now I'm going to use the quadratic equation solver on my calculator. That's that one. Polynomial degree 2. A is 4.9, B is minus 17.5, C is 15. And my solutions for t are coming up as 15 over 7. So remember, we've used g, so only 2 or 3 significant figures. So 2.14 seconds, or 10 over 7. So that's 1.42 seconds. Now, why have we got two solutions? Well, because one of them represents point P, and one of them represents the next time we're at this height of 15, which is point Q. So when the question asks us for how long are we 15 metres or more above O, well, we are for that height above O between 1.42 seconds, let's write that there, and 2.14 seconds. So the time we're above 15 is the difference between these. So 2.14 minus 1.42 is for a time of 0.72 seconds. There we go. Now finally, example 9. There's a lot of these, but I think it's really important for us to go through them carefully and make sure you understand these ideas. There's a ball struck at a point A, which is 2 metres above the ground. So we have, let's imagine this is the ground. And then let's get a different colour, that's a distance of 2 metres. So this is the point A. It's struck with a velocity of 5i plus 8j metres per second. So this is a little bit different to what you've seen already, because this time we are given the velocity in vector form rather than as a speed and an angle. So what we're told is this. So we've got 5i and 8j. We could from that work out the speed we're going at using Pythagoras. I'll show you here. Square root of 5 squared plus 8 squared is 9.43 metres per second. So it's being struck at 9.43 metres per second. But like I say, we're given it in this vector form. Let's sketch the projectile motion. There we go, something like that. It strikes the ground at B. So here's point B. So first of all, we've got to find the greatest height. So let's call this greatest height point, let's call it P. So we do see that from O to P. It's not O, is it? It's A this time. Tend to reserve O for something starting on horizontal ground because it's like the origin where we're starting. So A to P this time. S is a horizontal distance unknown, so we'll call it X, and a vertical distance unknown, so we'll call it Y. I'm going to mark my X and Y on here. Let's use a colour I haven't already. So let's take this one. X, you see that on the video, yes, and Y, there we go. So U is 5, 8. So there's no cosine sign involved here because we're already given those horizontal and vertical components. V, now remember at greatest heights, at any point along here, V is given by the tangent that we draw to the motion. So here, our V travels horizontally, but it has no vertical motion. And that's the important thing about the greatest height. A is 0 minus G, and T is unknown at this point. T would be how long it takes to get from here to here. No idea, we could obviously work it out. So in order to find this greatest height, they're asking us to find Y here, but there's a little bit more to it, and I'll point that out in a second. So we need to know this distance. So I need an equation that involves S, U, V and A. So that, of course, is my V squared equals U squared plus 2AS. Plug in our vectors. If I look on the top row here, I have two unknowns, v and x. That's no good to me at the moment. The bottom row, however, the vertical motion gives me 0 equals 8 squared, so 64, minus 2gy. So let's rearrange that. So that gives me y is 64 over 2g. 64 over 2 times 9.8 is 3.27 metres. Now be careful, because that's not your final answer. That is this distance. But the question is asking me for the greatest height above the ground. I didn't write it on here, but if you look in your book, you'll see it says that. So the greatest height above the ground is this y, which we've just worked out is 3.27, plus that 2 metres there. So it's 5.27. So the greatest height is 3.27 plus 2, 5.27 metres. Now, it wants us to work out the speed we're travelling at when we reach B. So just like we normally do, let's represent our speed as a tangent to the curve at that point. Now, because previously we were working from A to P, but now we're working from A to B, we need to do our CVAT again. The minute the part of the journey you're looking at changes, redo this. So S equals, now from A to B, do we know how far across is gone? Do we know the range of this journey? No, we don't. So we'll call that X again, an unknown X. So it's a different X to this one I've used here. This is now this X coming across here. That's why I've dotted it with the orange so you can see. However, vertically from A to B, we know that it's come down by 2 metres. So that's a minus 2. Our U remains the same because we're starting from the point A. Our V is what we're actually trying to find now. So let's give it our horizontal and vertical components. A is 0 minus g, and T, do we know the time of flight? No, we don't. So S, U, V and A. So let's have a look at how we're best to do this. Let's start with V squared equals U squared plus 2AS again, I think. Yeah, let's go with that. So we have got Vx and Vy both being squared, 5 squared and 8 squared, 2 and 0 minus g and x minus 2. Now you might be thinking, hold on, when we did this before we had two unknowns, but look, we've got 0 times an x. So on our top row we get Vx squared equal to 5 squared plus 2 times 0 times x. So that disappears. So that tells me that my horizontal component is 5. Then we'll find the vertical component using the bottom row. So Vy squared is 8 squared plus 2 times minus g times minus 2. So let's tidy this up. In fact, no, I'm just going to type it in. We've got the minus times the minus here, so that just makes it plus again. So we've got 8 squared plus 2 times 9.8 times 2. I can put both of these minuses in, but the minus times the minus just makes it positive, so I could have left them out. And that gives me 103.2. Oh, that's really, really fast going down. So it's not so much horizontally, but it's going very steeply down. I can see because that vertical component is much, much bigger than the horizontal component. Now, I haven't answered the question yet. What I've done is I have found this. We have a horizontal component of 5 and a vertical component of 103.2. The question asks me for the speed. Speed is not a vector. Speed is a scalar. Speed is the magnitude of this vector. which we can think of as the length of the line. So we're going to use Pythagoras on these horizontal and vertical components to find it. So our speed v is the magnitude of the vector v, and that's going to be the square root of 5 squared plus 103.2 squared, and that gives me 103. That's coming out really, really big. I wasn't expecting it to come out that big. What's going on? Let me think about this for a second. I think I've typed something in wrong. I know exactly what I've done. Haha, yeah, I know why it's come out so big. I'm really glad I made that mistake. Here, I got Vy squared is 103.2. I never square rooted it. Vy is therefore the square root of 103.2. This is the point where I would consider recording the video again, but it's so long, I'm just going to have it as a learning moment for you. There we go. It's worth pointing out, I noticed that that was far too big. It was coming out as 103, and 103 metres per second is far, far too huge. So it's worth pointing out that I noticed I'd made a mistake by thinking about the answer and thinking about whether it made sense. So that's better, 10.2 there. So our vertical component is 10.2 coming down, and that should be, let's just get rid of that, so that should be 10.2 there. So let's try this Pythagoras again. The square root of 5 squared plus 10.2 squared is coming out as 11.4 metres per second to 3 significant figures. There we go. That makes much more sense. That's much more reasonable. Okay, so on to the last part. It wants us to work out the angle that the ball makes with the ground when it hits at B. Now we're still thinking about the velocity here because it's the velocity that describes how it's moving. So we're still using this little diagram that I've done here. I'm going to draw it out again for this part because as it comes into the ground, here's the ground for you. We know that this part is 5 and this part is 10.2, not 103.2. I could write them this way around as well if I wanted to. So I could put 10.2 there if I liked and 5 across here. The angle it makes with the ground is this angle here. Let's call that alpha, shall we? So in order to find that angle alpha, I'm going to use the fact that we have a right-angled triangle here and that tan alpha is the opposite over the adjacent. So alpha is inverse tan of that. Remember in pure you call that arctan, don't you? So arctan of 10.2 over 5 gives me an angle of 63.9 degrees. Or 64 degrees. So we're hitting the ground with a speed of, where was it, 11.4 metres per second and at an angle of 63.9 degrees. Okay, now you can have a go at exercise 6C. Just bear in mind a few things that I mentioned to you and throughout this. Something like A is always 0 minus G. Anything going up is positive. Anything coming down is negative. Always give your horizontal and vertical components of S, U, V and A. And make sure that whenever a different part of the question requires you to look at a different section of the journey, like A to P here versus A to B here, redo your SUVAT because some parts of it will be different. And if you stick to those general principles, I think you'll be okay. Good luck, and I'll see you for the next video. Hopefully without any stupid mistakes like that one. Bye.